I'm now going to talk through AS Chemistry Paper 2, Specimen version 0.5. So I'm going to look first of all at question number 1. Question number 1, 1.1. Compound J, known as leaf alcohol, has the structural formula CH3CH2 CH2CH2OH, produced in small quantities by many green plants. The E isomer of J is responsible for the smell of freshly cut grass. Give the structure of the E isomer of J. Well, I'm actually going to do spoilers to start off with because you can see what it looks like. So the E isomer of J, if we actually look here, it's got a double bond between the two carbons. A structural isomer like this, an EZ isomer, sometimes called a geometric isomer, is part of a larger family of isomers called stereoisomers. So a geometric isomer is a stereoisomer, and it happens because of this double bond. So if you're asked why it happens, this double bond has no free rotation. Essentially it can't spin, and so it locks the positions of the other groups of atoms around it into space. But we say it has no free rotation. If you're asked for the definition of an EZ isomer, or a stereoisomer, or a geometric isomer, so EZ isomers or geometric isomers, part of the larger family of stereoisomers, the definition, not why it happens, but the definition is that they have the same structural formula, but a different arrangement of atoms in space. The different arrangement of atoms in space is a consequence of that double bond having no free rotation. So let's have a look at why we're saying this is the E isomer. What do? We look to the left of the double bond and we look to this carbon and we trace along to see what it's bonded to. It's bonded down here, it's bonded to an H. Up here it's actually bonded to that C. So you have a look at the two atoms that it's bonded to the left. This one is bonded to an H with a lower atomic mass, an atomic mass of 1. This carbon has an atomic mass of 12. So we put a ring around this and highlight it. We say this group here takes priority because that carbon joined to the C, as opposed to this H joined to the C, that carbon has a higher atomic mass. And then we look to the right hand side of the double bond and we look at this carbon here. This carbon here has an H bonded to it and a C bonded to it. So of the two atoms there bonded to this C here has got a higher atomic mass than the H. And so this group gets highlighted. This group has priority. So this group here and this group here have priority. They're opposite each other across the double bond, and so it's the E isomer. If this group were on the top, or the two groups taking priority were on the top or on the bottom, they're on the same side, and it would be a Z isomer. Just incidentally, one thing I didn't say is how do I check if this has geometric or stereoisomers at all? Well, I look to the left of the double bond on the carbon here. If this group and this group are different, and to the right of the double bond this group and this group are different, it will have geometric isomers. It only doesn't have geometric isomers if these two are the same or these two are the same. Draw the skeletal form of the organic product when J is dehydrated using concentrated sulfuric acid. Well, you've got to know what the word dehydrated means. Concentrated sulfuric acid removes water. The way that it removes water is, if you look at these two carbons here, on one side of the carbon it removes an H from there, and on the other side, the other carbon, it removes an OH. So it happens when two carbons have an OH on one side and an H on the other side of the two carbons, and when that H is removed and that OH is removed, it makes water, and between the two carbons you get a double bond. So let's actually have a look what's going to happen. We're going to have CH3 CH2 with a single bond between the two, a single bond then down to the C, a double bond between these two C's, a single bond down to this C, and after that H and that OH have been removed by the concentrated sulfuric acid and remove water, you'll end up with a double bond here. You'll have CH there and CH2 remaining there. So we're going to have single, single, double, single, double. 1, 2, 3, 4, 5, 6 carbons in a line, and it will look like that. So the way that we do a skeletal formula is we count the number of carbons, 1, 2, 3, 4, 5, 6. We put them in a zigzag shape, 1, 2, 3, 4, 5, 6. There's a carbon at every point on this line. We remove the H's, we never draw the H's, and the double bonds are single, single. There's the 2 singles. Then we hit a double bond. Then there's a single bond, that's that one there, and we've made a double bond between these 2 carbons. There it is, because we removed an H and an OH in making water when it's been dehydrated by concentrated sulfuric acid. Let's have a look at the next one here. So this one here, if I were to look at this, if I went to the left of the double bond, I've got a carbon joined to that carbon, and I've got a carbon joined to this carbon. That's an issue because both of those carbons have got the same atomic mass. So what do? I carry on further and have a look what these 2 carbons are joined to. Well, this carbon is joined to another carbon. This carbon is just joined to H's. So those 2 have got the same atom joined to this carbon, a carbon and a carbon, but when I go further along the bond, this carbon is joined to H's with a lower atomic mass than this carbon joined to a C, which has got a higher atomic mass. So we put a ring around this one because that carbon is joined to a carbon, this carbon is just joined to an H. This group here, called an ethyl group, this is a methyl group, 1 carbon, CH3, 2 carbons in a branch is an ethyl group. We put a ring around this ethyl group here, we say this takes priority. So the ethyl group takes priority over the methyl group. So now consider the groups joined to the right hand side or the left hand side. We've done the left hand side first. Consider groups joined to the left hand side of the carbon-carbon bond. Both groups contain carbon atoms, so go 1 bond further, and the carbon, this carbon here, is joined to another carbon, so this group takes priority, the ethyl group takes priority over the methyl group. To the right hand side we then look. This is actually easier because this carbon here to the right hand side is bonded to a carbon. This way it's bonded to a hydrogen, so this carbon having an atomic mass of 12 compared to the hydrogen only having an atomic mass of 1. This has a higher atomic mass than this, and so this CH2 OH group takes priority. We put a ring around that, and then we have a look and see which 2 groups have taken priority, which 2 we've highlighted. We've highlighted these 2. These 2 groups have taken priority. They're on the same side. They're both on the top of the double bond. They could be on the bottom of the double bond. They're on the same side of the double bond, and therefore it's a Z isomer. How do I then name it? How do I go about naming something? Well, first of all, I look at the longest carbon chain. 1, 2, 3, 4, 5 carbons in a row. So meth, eth, prop, bup, but, pent. It's pent. Pentane or pentene? Well, it's got a double bond, so it's pentene. Now then, let's have a look what else is joined to the pentene. I've got an OH called an ol. It's an alcohol, ends in ol. And I've got this group here off the main carbon chain. This is a methyl group. Which end should I start labelling from? Well, I've got to try and give the lowest numbers. I'm going to start labelling from this carbon here, this end, because then the ol group will be at carbon number 1, the ene will be at carbon number 2, and the methyl will be carbon number 3. So I can use a 1, 2 and a 3, a 1 to describe the ol, a 2 to describe the ene, where the ene is, and a 3 to describe where the methyl group is. So I'm going to label from the right hand side, because if I label from the left, numbers would be higher. Let's have a look and do spoilers on what it's called. 3-methyl, pent 2-ene-1-ol. I'll just talk about the fact that it's not ene, it's en rather than ene in a minute. Let's just look, let's just check. 3-methyl, yes, because 1, 2, 3, the methyl group is at number 3. On carbon number 2 is the ene, pent, 5 carbons in a row, 2-ene-1-ol. The ol, the OH group, is at number 1. So why have I lost an E? Well, if I disregard the numbers for a minute, I would have E-N-E-O-L. I'd have 2 letters next to each other. You disregard the number when you're looking at letters next to each other. And if I have two vowels together, an E and an O, I drop the E. That's just a rule, so that it becomes EN rather than EEN, because I'd have an E next to an O, and you can't have two vowels together. So 3-methyl pent-2-ene 1-ol. You could actually name that OH as a hydroxy group as well. So you could actually call it 1-hydroxy 3-methyl pent-2-ene and keep the ene as a group. Either would be allowed.